and understanding of physiology is very important because it will help you out in terms of evaluation, management, and overall pathophysiology in that regards. So today we'll talk about the basics of endocrine physiology. What really is an endocrine gland? What are hormones? How do they act? How do they interact? And in that, we'll also put some case scenarios to really highlight the interaction between physiology and how this physiology helps you identify in terms of pathophysiology. Hormones are unique compounds which are really going to help out in terms of bringing out actions from a distant site from the site of production. So what really is a hormone according to you, Dhwani?
Hormone is a chemical compound that has an action distant from the location of the gland.
Yeah. So you said three things. You said it's a chemical compound which is having action which is distant from its site of production. Anything else? So any compound which is being produced from somewhere and acts distantly becomes an hormone. So N is negatively corrected by a particular compound. So calcium is produced by bone, which acts at the parathyroid gland to suppress PTH. And if the calcium becomes too much, the calcitonin suppresses calcium secretion. So it's being produced by bone, which theoretically can be a gland, acts at a distant state, and it is suppressed negatively. Is calcium a hormone? So what do you think is this thing which the clue in terms of that you will not consider calcium a hormone? So you didn't mention about small, and many of these compounds are very small. So one key parameter is non-nutritive signal. So otherwise you will start thinking of sodium, everything will become a hormone. So it's a non-nutritive signal which is produced at one point of the point and then it acts on a distant point. Now you talked about gland. So leptin is produced by a adipocyte and then it is going to act at multiple places. Most important site of effect of leptin is in the central processing unit. Is leptin a hormone? Although it is being produced by a fat cell. So this concept of having gland again becomes a very, very difficult scenario. So we don't need to have really a gland. You can say the whole fat is a gland. So this becomes important. So is bone a gland? Would you consider bone as an endocrine organ?
Yes, sir. Produces the...
So can you think of something which are produced by the bone which act distantly? That is paracrine. It doesn't work on that. Something which is now being used in treatment of short stature. It is produced by CNP. So C-type natriuretic peptide, that is one thing. Then of course, bone can also produce osteocalcin, which has got distant effect. Bone produces, we know a lot of substances, rank, ligand. So all these things are coming from bone. FGF23 is being produced by bone. So clearly now we know that we have now tried to counter three specific things. One, we don't consider small nutritive signals as hormones. That is one thing. Second, our definition of what is a hormonal gland has changed. So you can include bone as a clear-cut criteria which is considered to be an endocrine gland. Intestine produces GLP-1 which is going to act on the brain. So it can also act as an endocrine organ. Heart produces atrial natriuretic peptide which causes the thing. So now we need to understand that the concept of hormones is not restricted to those 7 or 8 glands which are there in the body. It is much more broader. Although when you talk about endocrinology, we are largely focusing about these things largely, but you need to understand what really hormones are from that perspective, and that becomes important. So hormones are essentially communicators, and when you talk about communication, we have got two types of communication, neural or endocrine. Neural is point to point. This is from here to there. So you have got either a synapse or you've got the neurochemical junction which will provide the signal, while hormone will provide you a distant regulation from the site, as Dhwani had mentioned in that regard. So they go from one side, acts through the bloodstream to a different thing, and then they act on that regards. Now, the importance of hormone is illustrated by the fact that all the hormones in the body, if you really collect everything and you crystallize them, it will be like 5 grams. It will be like a 1 spoon, and this 1 spoon is controlling so many systems in the body. So they are extremely important from that perspective. So endocrine system, we know, control different aspects, and these include short processes, acute processes, and chronic processes. So you have got calcium, bone strength, volume and salt, glucose, growth, puberty, and thermogenesis. So now if you talk about these scenarios like calcium, glucose, volume and salt, and thermogenesis, these are acute scenarios. So you want here the hormones to respond immediately to environmental stimuli. They should be released immediately and they should act immediately. While for bone strength, growth, and puberty, the hormones which are controlling them need not be reacting immediately. They should actually wait and watch and see if your body is in a situation to respond, and then have a gradual impact from that perspective. So what will be the distinct differences in hormones which are controlling, let's say, volume, salt versus growth?
The ones regulating the acute processes need to be prepared in advance so that they can
Yes.
release as and when required. Whereas those that are controlling more chronic processes may be slowly processed when required.
So the regulation of large hormones which are responsible for acute control should be done at the level of release. The classical example is large, I'm talking about large hormones. If it's a small steroid hormone, you can prepare immediately. You can't control it on that perspective. So large hormones which require immediate work is insulin, PTH, AVP. So all these hormones you cannot make. Okay, somebody says your sugar is going up, now I'll start producing insulin. So this is not something which is going to work on that. You need to keep your insulin immediately. Suppose you have got, you are the defense minister, so you can't say that when the war happens, I will then make all the weapons start. You need to keep it in a depot. So similarly, if you have vasopressin, if you talk about parathyroid hormone, if you talk about insulin, they are all made, ready-made, packaged in the vesicle and kept. Now, why don't you keep cortisol, aldosterone? These are also acute hormones. Why don't you keep them stored in the cell? Why do you synthesize immediately? So when you have a stress response, what is produced? Which hormone is produced? First, epinephrine, that's there. But in terms of the regulatory hormone, which comes? CRF, then ACTH. Then what does ACTH do? To synthesize and not release. So why don't you store cortisol? Why don't you store aldosterone? Like you're storing AVP and you're storing your all the other insulin, PTH. You cannot store because they will pass, they will escape. So you cannot store these hormones, and that's why they are small hormones you can immediately synthesize. So in acute regulation, we have talked about two types. Peptides are there stored. So there is a mechanism is largely controlled at the level of release. So when we talk about disorders of insulin production or insulin deficiency or excess, we are talking about problems of insulin release. So we talk about potassium ATP channel defects. If your potassium ATP channel defect is working too much, you will have a scenario of different. You will have hyperinsulinism. If it's not working well, you will have diabetes. So this is how it will be controlled. But if you talk about long-term scenarios like growth, puberty, or bone strength, these will only happen when you have got enough nutritional status in the body. If the body is in an undernourished state, it will never want to go for growth, puberty, or reproduction, because these are the scenarios in which you are using your energy. So this will depend upon, and then you will say, okay, I will now start producing growth hormone. I will now start producing your estrogen or testosterone, or from bone health perspective, other hormones on that regards. So these are crucial and they link nutrition and metabolism, and often this interaction becomes important between physiology and pathology from that regards. So when we talk about chemical messengers, their action will depend upon how much far they are going to act. So if you have a substance which is secreted by the cell, it goes into the blood, and from there it is going to act at a distant part. This is the classical endocrine system. You may have a system in which it may act at a local level. It is being produced there and act locally. that will be the paracrine effect, or it may affect the cell itself, in which it is known as the autocrine effect. So these three scenarios are there. What is the difference between paracrine and endocrine effects? What are the key differences?
Endocrine is producing somewhere else and going to the
No, that is obviously, that's the definition. So in terms of the conceptually, what are the difference?
concentration is required much more. We have to travel a long distance.
Yes.
For the paracrine, there the concentration is usually less than the endocrine.
So you need to have, not in the systemic circulation, the concentration is to be there, but in the local level, the concentration may be more. So what is essential for a paracrine effect is that you need to have something to keep that hormone in that particular region. Otherwise, it will leak out. So either you have some mechanism which is acting like a boundary, or you have a binding protein. Now, when I'll talk about binding protein in more detail, we'll say that binding proteins are largely required for which type of hormones? Steroids. Because steroids are lipophilic. So they will not go into the circulation. You need a binding protein. But peptides who are acting as a paracrine effect, you will need to have clearly a scenario of a binding protein. The classical example is IGF system. So you've got IGF-1 and IGF-2. Now, IGF-1 will also have a systemic effect. It is being produced via the growth hormone acting on the liver to produce IGF-1, which will work, but it will also be locally produced. And the local action will depend upon how much is the binding protein level. So if your binding protein level is low at a local level, what do you expect in terms of the cellular growth, and what could be the adverse effect of that?
That we have more free counts.
Yes. So more for IGF-1 perspective.
But this more IGF would also be good.
Yes. So this is an important concept. So binding protein deficiencies may also be a predisposition towards development of malignancy. So binding protein is not just a simple thing, passive thing. It has an active role which happens in that perspective. Same hormone can have a endocrine, paracrine, or autocrine effect. So if you say growth hormone is being produced via the somatotropes, it will of course have an endocrine effect. It may also have a local effect, and it may also suppress the growth hormone production. So the same hormone can have all these effects, which becomes important. So when I talk about paracrine signaling, you have got the particular signal which is restricted to that place. You don't want to allow it to go out, because then it is going to be diluted and it is not going to have much effect on that regard. So it's a localized one. It cannot go out from that regards, and this is very tightly regulated, and it's responsible for selective action. Many times, similar receptors may have distinct effects depending upon the ligand which is there. So can you talk about a particular scenario in which the ligand, different receptor, same receptor, different ligands, they have a different autocrine, paracrine, or endocrine effect? So there are two compounds who have got same receptor. One of this is working through the endocrine pathway, causing a different systemic regulation. The other one is acting through the same receptor into a paracrine pathway, having different. So yes, so type 1 PTH receptor is acted upon by the parathyroid hormone, and it will work in terms of a systemic function, endocrine, causing high calcium, low phosphorus, while PTH like related peptide will cause local growth, and that is why it is involved in the chondrocyte development from that perspective. So this also becomes important. So when we talk about endocrine signaling, and we will use this as a template when we talk about endocrine pathology, is that the first thing is that signal is produced by the hormone, by the gland. It then has to go into the circulation, because this is the way it will go forward. Here, it is going to go to different areas to have its action. And also, it may have multiple sites of action in which it would also have a feedback mechanism which would be there. There will be local modulation of that particular hormone. And we'll talk about local metabolism being extremely important in terms of effects. Now, can you talk about some common pro-hormones which we consider as hormones? So some hormones which conventionally everybody says they are hormone, but they are actually pro-hormones. Yes. So testosterone is clearly a prohormone. It has to be either converted to estrogen to have an effect or dihydrotestosterone to have an effect. Second, so what I'm trying to, in other words, I'm trying to say that the primary product of the gland, which is actually a prohormone. So testosterone from testis. Then thyroid gland, T4. T4 is actually a prohormone. It has to be converted locally. So you need to have a mechanism by which it has to be metabolized locally, and then only it is going to be acted upon from that perspective. So this signal will also be then inactivated at a distinct amount. Now, other thing to remember is that you have got the same hormone level. If somebody has got a growth hormone level of, let's say, 7 nanogram per ml, every part of the body will have the same growth hormone concentration. So every tissue will be exposed to same growth hormone. But some regions will respond to growth hormone, like you will have cartilage which will grow. Some regions like adipocyte may respond a bit less, but they will respond. There may be some regions which do not respond. So what decides the selectivity, Dr. Vibha, about the hormone action? When they are exposed to the same concentration. So whether you have got the receptors or not. Second,
the local enzymes,
local metabolism. Third,
available concentration at a particular site.
which is decided by? Yes. So the same level of hormone will have different effect in different parts, because one, of course, you've got vitamin D, which is high, but one region doesn't have a vitamin D receptor, so it is not going to work. Second, as you very nicely said, that maybe the vitamin D binding protein will take that compound to a particular area. Okay, I want to take it to the bone, and then only it is going to work there. Third, there may be inactivating enzymes which are there in particular areas, which where you don't want that particular action, you will remove it from that perspective. The classical example of that is the 11 beta HSD system, which basically converts cortisol into cortisone. So it is inactivating cortisol on one way and activating cortisol to cortisol on the other direction. So in tissues where you want cortisol action to be there, you will have the 11 beta HSD1 activity predominating, which is going to convert your cortisone to cortisol. While in tissues where you wouldn't want this cortisol activity to be high, you will have the 11 beta HSD2 activity, which is converting cortisol into cortisone. So these all things become important. So the selectivity, one aspect which we talked about is receptor, second aspect is binding protein, third is local metabolism, which becomes important. So that's why you need to have a specific thing. Now, the other thing to remember is that there is also a multitude of effects. One hormone can have a multiple effect. So if we go by a classical example, the growth hormone, we know the classical signaling is growth hormone IGF-1 axis. So the somatomidin hypothesis, which basically says that growth hormone acting on liver produces a IGF-1 using the growth hormone receptor. We'll talk about the receptor action later on. And this is going to bring down the IGF-1, and this IGF-1 is going to cause the growth. So this is how you will do. But if you compare the different knockouts, so suppose you have got a knockout of growth hormone versus a knockout of IGF-1 versus a knockout of IGF-1 receptor, would you have a similar phenotype or a distinct phenotype?
Starting straight from birth, where
Yeah.
IGF-1 and IGF-1 receptor defects have shorter,
Yeah.
smaller babies at birth, whereas
Hmm.
GHD babies will have a
So GH or GH receptor will not have an abnormality in birth weight. Why, Ashutosh? Why is growth normal in what controls growth in the antenatal period? Insulin, yes. So insulin, IGF-1, they are the major regulator of growth, with growth hormone and thyroxine not playing a role. So what Dr. Dhani is saying basically is that because you have got a problem in the growth hormone or growth hormone receptor, your phenotype will be normal at birth. While those who have a problem in IGF-1 gene or IGF-1 receptor will have a different behavior. Second thing, of course, is that if you compare somebody who has got zero IGF-1 and he is growth hormone deficient, very low IGF-1, growth hormone deficient versus growth hormone resistant, will they be same?
respond,
No, of course, I'm not talking about response. I'm talking about phenotype. So those who are growth hormone deficient will have a different facies as compared to those who have a growth hormone insensitivity. Insensitivity will have more of sparse hair, coarse features, and more of frontal bossing. So what it tells you is that there is a growth hormone effect which is independent of the growth hormone receptor. That means growth hormone also has a direct effect, and that's what the multitude of hormonal effect is there. So now this is the endocrine effect. Now, on top of this, growth hormone is going to have a direct effect on the growth hormone receptor in the skeleton. So it is going to then stimulate the IGF-1 production, which is local, to cause those effects, which is paracrine. And then, of course, we know that IGF-1 will have a direct effect on that regards. So therefore, when we are deciding a particular therapy, we have to be clear that which one is better. So if you have growth hormone deficiency, why don't you give IGF-1? Why do you give growth hormone?
We have all the three pathways. Can increase the IgM1 level at the level of 1% by using paracrine pathway also. That is 1% in IgM. But IgM1 has also tumorigenesis like.
So, but you are increasing IGF-1 with growth hormone also. So when you're giving growth hormone, you're increasing IGF-1. Won't that be tumorigenic? Why? Yes. So with growth hormone, you are increasing both IGF-1 as well as IGF binding protein 3. So because of that, your free IGF-1 doesn't search. So that's an important aspect. Third, very important is, yes, IGF-1 can act on the insulin receptor to cause hypoglycemia. So these becomes important. Now, what you also need to remember, this is what I discussed earlier, is that you may have, so one I said, one hormone acting at different sites. Multiple hormones acting at the same receptor may also happen. This is the classical example of type 1 PTH receptor, wherein you have the PTH which is acting, which is causing predominantly the endocrine effect. And here it is going to act on the bone to cause release of calcium, acting on the kidneys to increase 1-alpha hydroxylase activity, increasing calcium absorption, increasing phosphate resorption. These things will be there, while PTH-related peptide is going to act mainly on the chondrocyte to cause a local or a paracrine development in that regards. So if you have somebody, Dr. Vibha, with hypoparathyroidism, what will be the skeletal phenotype at birth? Yes, but if you have a Bloom-Stans disorder, what will happen? Yes, so this is very important. So PTH deficiency, no PTH resistance, they'll be normal at birth. But if you have a problem in the type 1 PTH receptor, your skeleton will be completely in a very bad shape because your PTH-RP can also not act. So PTH-RP is responsible for fetal bone chondrocyte development, while PTH is involved more in terms of postnatal calcium. And why is if suppose you don't have any calcium, PTH, Ashutosh, how will the baby's calcium be maintained in the intrauterine period? So if your PTH is not there, your calcium should go down, but the baby will not develop hypocalcemia because calcium is coming from the mother. So mother is continuously supplying calcium. So you don't have, the fetus doesn't have a pituitary, doesn't have a thyroid, doesn't have a adrenal, doesn't have a parathyroid, doesn't have a all these things doesn't matter because glucose is coming from the mother, calcium is coming from the mother, warmth is coming from the mother, sodium, potassium are being managed by the mother. She is actually taking that. So all these hormones will have limited role in the antenatal period, and this we'll discuss about in perinatal endocrinology when we talk about it. So this becomes important. So now, as we discussed, we have got a compound which is going to act at the particular receptor. So you have the endocrine gland and the target organ. Now the target organ will also produce something. It may be IGF-1, it may be CNP, which is then going to act on the primary organ. So this becomes important. What is a target organ and what is the primary organ? But what we are going to do today is that we mainly talk about the classical endocrine systems so that we don't get too much into all those conflicts. So I'll talk mainly about these symptoms: the pituitary, the thyroid, the pancreas, gonads, parathyroid, and adrenal. So these are the core as far as the endocrine glands are concerned. The novel areas we will not be focusing too much from that perspective. But we need to understand that brain also can be considered as endocrine organ, it produces brain-related natriuretic peptide. If you have too much BNP, you will have salt wasting, and this is known as cerebral salt wasting. Bone, I said osteocalcin, FGF23, and CNP. All those things can be produced from the bone. Fat will produce leptin, adiponectin. Heart produces atrial natriuretic peptide. Intestine produces GLP-1, and kidney produces renin. So nearly every organ can be considered as an endocrine organ, but we are focusing on mainly the classical endocrine organs. Now, we talked about how the same hormone is having multiple effects, how multiple hormones act on the same receptor. Now, same hormone can have different effects, and that's why you will have pleiotrophy of presentation. Now, if you look at Cushing syndrome, a person with Cushing syndrome will have short stature, will have obesity, will have plethora, will have myopathy, will have hypertension. So they can come with any of those presentations. So you need to understand that it's not just that this is going to cause everything. Same with thyroid. The same thyroid gland is affecting bone strength, brain function, cardiac contractility, cardiac tone, thermogenesis, growth plate, and motility. So what it tells us is that the presentation of endocrine disorders can be very varied, and same disorder can present. So hypothyroidism can come to you with developmental delay, with hypothermia, with precocious puberty, with delayed puberty, with ovarian cyst, with hyponatremia, with dyslipidemia. So you need to keep your eyes and ears open about endocrine disorders. Some things like growth hormone deficiency, you know, okay, main problem will be height, will definitely be affected, but it's not true for all the hormones. The other important thing is redundancy. So in what sort of conditions, Swani, would the body want to be redundant in terms of hormones? Yeah. So what do you mean by redundancy?
Multiple hormones are working to ensure a same target.
So if you talk about a particular homeostatic condition, like let's say a blood glucose level, there will be ways in which if the sugar becomes too much, you want to pull it down. If the sugar becomes less, you want to pull it up. So the body will have to decide what is more important for it. So if your sugar is low, that is of course more dangerous, because the way humans evolved was there a time when we didn't have much to eat. So there are 4 mechanisms which are countering hypoglycemia, while there is only one mechanism which is countering hyperglycemia. So what we are trying to say is that growth hormone, cortisol, epinephrine, glucagon, they are all 4 acting on that. So if you have one defective, suppose growth hormone is not there, doesn't matter, glucagon is going to work. If both are not there, epinephrine is going to work. So if you have got multiple friends, you have got 4 friends, one of them doesn't come to help, others will help out. But if you have only one, then of course you will have a more greater problem which is there. So that is why, what is more common, hypoglycemia or hyperglycemia? From a human perspective, what is more common? Huh? Hypoglycemia is more common. So you see so many patients with type 2 diabetes, type 1 diabetes. So no fluid is a different thing altogether, but still you will not develop hypoglycemia for a long time because body is developing. But if you have too much, you will develop hyperglycemia. So all these mechanisms have evolved over time in circumstances of deprivation. When you have got low amount of glucose, low amount of sodium, low amount of temperature, low amount of sodium, calcium, and everything. So if you talk about sodium now, so what all hormones are increasing sodium? Yeah. So renin, aldosterone, cortisol, what else? AVP, what will it do? It will save water. It is basically save water. Sodium, it will have, it's mainly working from a water perspective. How many are there to decrease sodium? ANP. So that will be only one, and that's a weak hormone, while your aldosterone is a predominantly strong hormone. So anything which is more dangerous for the body will have more protective mechanism. What about calcium? So calcium, yeah, via and decrease via PTH and vitamin D. Okay. Yeah. FG23 decreases calcium. No.
That's a phosphate.
So what is there? So calcitonin. So which is stronger? So you need to understand which way you want to avoid. So if you want to avoid hyponatremia, avoid hypocalcemia, avoid hypoglycemia, you need to have a strong system to boost up. That is why you got the redundancy. So even if you have one or two defects, you are okay. So why I'm talking so much is that what it means is that if you are developing hypoglycemia because of an endocrine deficiency, it is going to be there because of multiple hormone problems. It cannot happen with a single hormone defect. So growth hormone deficiency or isolated cortisol deficiency should not cause hypoglycemia. Extremely rare situations they may, but for the argument's sake, they do not cause hypoglycemia. While if you just have a high insulin alone, you will have hypoglycemia. So this redundancy is an important aspect. So insulin is there to counter 4 because body did not develop hyperglycemia, then we didn't have enough food. But now when we got so much fluid, you have only one hormone to counter. That's a problem. That's why the diabetes and everything have become more.